Good evening, students. Audibility is okay.
Yes, sir.
So thanks. So welcome in next lecture of Math F212 optimization. Presently, we are doing the transition of graphical solution to the algebraic solution. So in that, we have seen how to handle the constraints, what should be the characteristic of the variables. So in the next question, so this is the famous question, the Radimic problem. The Radimic produces both interior and exterior paint from the two raw material M1 and M2. The following table provides the basic data for the of the problem. So here we have the how much tons required for the production of exterior and interior paint of from the material M1 and M2 and what are the profit. The market survey indicates that daily demand for interior paint cannot exceed that of for the exterior paint by more than 1 ton. Also, the maximum daily demand for interior paint is 2 tons. Radimic wants to determine the optimum product mix for the interior and exterior paint that maximize the total daily profit. So, this is a very famous question. We have already done its graphical solution, its formulation. So, let us discuss one by one. So, this is the formulation. Maximize z is equal to 5x1 plus 4x2 subject to 6x1 plus 4x2 less than equal to 24, x1 plus x2 less than equal to 6, minus x1 plus x2 less than equal to 1, x2 less than equal to 2, x1 x2 greater than equal to 0. So there are total 5 or you can say 6 constants. There are total 6 constants. Means this is the fifth one and this is the sixth one. So when we draw the graph of this, so we have the graph of this problem is like this. So where we know that at the C we have the optimum solution. So this much you know. So in this case, when we are transiting the graph solution from when we are transiting the algebraic solution from the graphical solution, we have to convert all the inequality in the inequality form using the proper slack or surplus variable. So in the first constraint, we have added the select variable. In the second constraint, we are added the select variable. In the third, we have added the another select variable. In the fourth, we are adding here the another fourth one select variable. So now presently we have the total four equation m is equal to 4 and total n variable x1 x1 x2 s1 s2 s3 s4. So total n variable. So from the theory we know that n minus m variables we consider as a non-basic variable. So n minus m will be the 2 and number of the basic variable which form the basis. So that is the m is equal to 4. Means whatever the number of equation that much variable we have to take. It may and now if you compute the basic solution. So how many basic solution we have? NCM. Total NCM. So here we have the 6 is 64. So it total we have the 15 basic solution. So how they will come? Let us see. So here if you assume x1 x2 as a non-basic variable, the second column is the non-basic variable. If you assume the x1 x2 as a non-basic variable, so remaining 4 s1 s2 s3 s4 will be the basic variable. So when we say non-basic variable, it means x1 is equal to 0, x2 is equal to 0. So when we put x1 is equal to 0 here, right, x1 is equal to 0 here, if you put the x2 is equal to 0, then what will come? S1 is equal to 24, S2 is equal to 6, S3 is equal to 1, S4 is equal to 2. So that will be the our basic solution. So here we have the basic solution. Similarly, when we assume x1 is equal to 0, s1 is equal to 0. When we assume x1 is equal to 0 and s1 is equal to 0. So now we have the system of equation with variable x2, s2, s3, s4. Clear? So from here we can compute the value of x2, s2, s3 and s4. So you will get 6 minus 6 minus 5 minus 4. What we want? We want all the variable must be non-negative. So here we have the some variables are negatives, right? Some variable are negative. That's why we say the solution is infeasible. First one is the feasible solution. This one is the infeasible solution. Similarly, for the non-basic variable, this following are the basic variable. So here we have the infeasible solution. 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 Here we have infeasible solution, infeasible solution, infeasible solution, and rest are the feasible solution. For the feasible solution, we will compute the value of the z from the 6x1 plus 4x2. No, 5x1, 5x1 plus 4x2. From here, we compute the value of the z for the feasible solution. So it will come 0, 4, 20, 21, right? 18 and 13. So here you can observe. Here you can observe that, right? Here you can observe that it is the maximum. So here we say it is the maximum. So from the graph, if you want to correlate this solution, so here we have the point A, means x1 is equal to 0, x2 is equal to 0. See, this is the line. This is the line of x2 is equal to 0. This is the line of x1 is equal to 0. So here, in the first we say we add the s1. So first one is nothing. It is the line of s1 is equal to 0. When s1 is equal to 0, then only we have the 6x1 plus 4x2 is equal to 24. That's why this is the line of s1 is equal to 0. When we add here the s2, so it means s2 is equal to 0, then only it is the line of the x1 plus 2 x2 is equal to 6. So here it is the line of the s2 is equal to 0. Here we have the line of the s3 is equal to 0, and this is the line of the s4 is equal to 0. Right, s4 is equal to 0. So different coordinates we will get. So here we have the x1 x2 is equal to 0. Then after n, x1 is equal to 0, s1 is equal to 0. So x1 is equal to 0, s1 is equal to 0. The point is the n. x1 is equal to 0 and s1 is equal to 0. In this, I have not drawn. So this is the point n, right? This is the point n. So you can observe this point is what? It is the infeasible point. It is infeasible point. And this point is what? This is the feasible point. This is feasible point, right? This is the feasible point. 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 And here we have the feasible point. So these are the feasible point. All other are the infeasible point. All other are the infeasible point. All other are the infeasible point, right? All other are the infeasible point. So total if you count, there are the 15 combination, right? So here we have the first, second, third, fourth, fifth, right? Some are infeasible, some are infeasible. Fifth, then we have the 6, 7, 8, 9, 10, 11, 12. 11, 12, something remain. I think this remain 13 and 14. 13 and 14. So now which one is the fifth one? Which one is the fifth one? So here you can see, here we have the line parallel to the x-axis, So it cut at the infinity. So here we have written, right? So this will be the 14th one. So total 14 point we have drawn on the graph, and parallel line solution will come as a infinity, right? Parallel line solution will come as a infinity. So that point we cannot mention. Here. So this is the little bit about the graph and algebraic solution. So any doubt in this part? To understand the graphical solution, what is the non-basic variable, what is the basic variable, what is the basic solution, feasible solution, infeasible solution, what are the points A, N, K, F, why we have the infinite solution, why we are not able to say the point. It is clear now. Let us have this question. Show graphically that all the basic solution of the following LP are infeasible. So maximize z is equal to x1 plus x2 subject to x1 plus 2x2 less than equal to 6, 2x1 plus x2 greater than equal to 6. So when it is the x1 is equal to x1 is less than, so here we add the slack variable x3 and here we subtract the surplus variable x4. Right. So this is the graphical solution. So here you can see count how many intersection point we have: the 1, 2, 3, 4, 5, and this one is the 6. So total means here we have the m is equal to 2 equation, n is equal to 4, x1, x2, x3, x4. So n minus m will be the 2. That is the non-basic variable. So so 2 are the non-basic variable. So 2 will become the basic variable. 2 will become the basic variable. So total number of the point will come NCM. That is the 4C2. That is your 6. That is your 6. So total 6 points we have. So 6 point on the graph we have drawn here. For this problem, 6 points we have drawn. And if you see the table wise, so here if you take this as a basic variable, so remaining one are the remaining one are the non-basic variable, right? So if we are saying that x1 x2 are the basic variable, so it means non-basic variable will be the x3 x4. X3 x4 for the x1 x3 it is the x2 x4. For the x1 x4 it is x2 x3. For the x2 x3 it will be the x1 x4, and for the x2 x4 it is the x1 x3, and for the x3 x4 it is the x1 x2. So when we put x3 x4 as a 0, x3 x4 as a 0, so when we put x3 x4 as a 0, this you put 0, so here you have the equation, two equation. So from the two equation you will get the solution: x1 is equal to 26 by 3, x2 is equal to minus 4 by 3. So here we have the solution. So here you can see x2 is coming negative. Here you can see x3 is coming negative. Here you can see x4 is coming negative. Here you can see x3 is coming negative, x4 is negative, and x4 is negative. What we want? We want x1, x2, x3, x4 should be non-negative. So this will give you the infeasible solution. So here all the points are infeasible. So from the graph also, if you will see in the graph, one region is this side, another region is this side. So there is no intersection region in the first quadrant. That's why we have the infeasible space, right? We have the infeasible space. Then we say we have the no solution. So for this problem we haven't the no solution. Yes, any doubt? These questions are very easy question, but there are a lot of concept in here. May I proceed further? Yeah.
Sir.
Next question. Consider the following LP. Maximize z is equal to 2x1 plus 3x2 plus 5x3 subject to minus 6x1 plus 7x2 minus 9x3 greater than equal to 4, x1 x2 x1 plus x2 plus 4x3 is equal to 10. So in this case it is given to you x1 x3 greater than equal to 0, but x2 is unrestricted in sign. So when the x2 is unrestricted in sign, we replace the x2 as a x2 minus minus x2 plus, where the x2 minus and x2 plus are non-negative. So, and here we had the or subtract the surplus variable. So it will come maximize 2x1 plus maximize z is equal to 2x1 plus 3x2 minus 3x2 plus 5x3 subject to minus 6x1 plus 7x2 minus 7x2 plus minus 9x3 plus or minus x4 is equal to 4 and and x1 plus x1 plus x2 minus x2 plus, very important question, please let's see carefully, plus 4x3 already in equation form, no need of the slack or surplus, is equal to 10 and x1 x2 minus x2 plus x3 x4 all are greater than equal to 0. Now, so here we have the m is equal to 2, n is equal to 5, x1 x2 minus x2 plus x3 x4. So n minus m will be the 3, that much is the non-basic variable. So basic variable will be the 2. So for a moment if you assume x1 x3 x4 are the non-basic variable, if they are the non-basic variable, then the equation means these are equal to 0. So when these are equal to 0, our equation reduced to 7x2 minus 7x so here you will get the 7x2 minus 7 some x2 plus, right? This will come 7x2 minus 7x2 plus is equal to 4 and another equation will come x1 plus x2 minus x2 plus is equal to 10. So what will be the value of x2 minus and x2 plus? What is the value of x2 minus and x2 plus? What is the value of this from this system of equation? This is the inconsistent. So simultaneously both cannot be positive. Simultaneously both cannot be positive. Simultaneously both cannot be positive. One should be the right 0. So either we have the x2 minus positive, right? Then x2 plus is equal to 0, or we have x2 minus is equal to 0 and x2 plus is greater than 0, right? We can have this, or we can have both can be 0. x2 minus is equal to x2 plus, both can be 0, but both cannot be positive. That is the conclusion of this question. So here we have converted into the equation form. Here if you assume x1 x3 x4 as a non-basic variable, so it will give you, so it is since 7x2 minus 7x2 plus and x2 minus x2 plus are dependent, it is impossible for x2 minus and x2 plus to be the basic simultaneously. Both cannot be basic simultaneously. Only when we deal with the unrestricted variable, so in dealing the unrestricted variable, we use the two non-negative variable. So both non-negative variables simultaneously cannot be the basic variable. That is the conclusion of this problem. Clear? At a time only one variable will be the basic variable. Consider the following LP. Maximize z is equal to x1 plus 3x2 subject to x1 plus x2 less than equal to 2 minus x1 plus x2 less than equal to 4. X1 is unrestricted. When we say x1 is unrestricted or x1 is unrestricted, it will be the x1 is equal to x1 minus x1 plus, and x2 are the non-negative. X2 are non-negative, and x1 minus and x1 plus both are the non-negative. Determine all the basic feasible solution of the problem. Use direct substitution in the objective function to determine the best basic solution. Solve the problem graphically and verify the solution obtained in C is the optimum. So what is the problem? Here we add the slack variable, right? Slack variable. So let us check whether we have taken the x3, x4. Okay. So here we add the slack variable x3. Here we add the slack variable x4. So now we have the m is equal to 2, n is equal to 4, n minus m is equal to 2. That much we have the non-basic variable. So m is equal to 2 will be the basic variable. So total we have the and and x1 is unrestricted in sign. So when the x1 is unrestricted in sign, it will become the 5. So it will, in that case, it will become the 3, and basic variable will be the 2 only. So 3 are non-basic variable and 2 are the basic variable. So if you take the any 2 combination, so these are the basic variable. So you take x1 x2, x1 x3, x1 x4, x2 x3, x2 x4, x3 x4. See, there is one thing is given to you, x1 is unrestricted. So when x1 is unrestricted, either you tackle like this, or you compute, and if x1 is coming negative, then also it is a feasible, because x1 is given to you as a unrestricted in sign. X1 is coming negative, then also it is feasible because x1 is the negative. But x2 is given to you non-negative. It cannot come the negative. That's why here we have the infeasible solution. So graphically you can see x1 can take negative value also, positive value also, as well as the 0, right? As well as 0. So on this side we have the graph. On the left side of the first quadrant, or in the second quadrant also we have the graph. And when we compute the optimum value will come minus 1, 3, and here also optimum value will come at the minus 1, 3. So either you compute algebraically or through the graphically. You have to take care how to deal with the unrestricted in sign variable. Now next we have to move to the very important part of the simplex method. Simplex method is iterative in nature, means we will start always iteration from the origin. Then we move in the direction of maximum improvement. Wherever we have the maximum improvement, in that direction we go in the further iteration. And always we go corner to corner. Because we know that all others in LP, the optimum solution or the solution exists at the corner point only. So we go right corner to corner, but through the edges. Never we go corner to corner through the diagonal. Always we go through the edges only. And these type of the movement are known as the iteration, right? So in each iteration, we know that for each solution, for each corner point, for each solution, for each iteration, we know that few are non-basic variable, few are basic variable. So with that, we decide the entering variable, which one is the entering variable, which one is the leaving variable. Means entering variable, here we have the non-basic variable will become the basic variable, and leaving variable means basic variable will become the non-basic variable. So in the basis, which variable will come in the pool of the basic variable, which variable will come, that will be the entering variable, and which variable will leave, that will be the leaving variable. because number of the basic variable in a pool, right, in the basic always with a constant, that is the small m. So let us have the consider the graphical solution of Radimic model. So this is the graphical solution. Identify the path of the simplex method. So in this side, here we have the objective function 5x1 plus 4x2. So if you increase the x1 by unity, so there is total increase in the profit is the 5. If you increase the x2 by unity, there is the increment of the 4 unit, right, in the profit. It means maximum improvement in this direction, maximum improvement in this direction. So we start from the origin and move in the direction of x1 because x1 give the maximum improvement. Then if we go from corner to corner through the edges, we go from the point A to B through the edge AB, then B to C, then B to C through the edge BC. Clear? So this is written here. We have started from the origin on the direction of the largest rate of the improvement, means in the side of the x1 we move. Now we move from the corner to corner through the edges, and this is known as the iteration. Then we have to decide which one which one is the entering variable, which one is the basic non-basic variable, right, or a living variable. So here when we say a, so a point means here we have the x1 is equal to 0, x2 is equal to 0, x2 is equal to 0, and x1 x2 is nothing, they are the non-basic variable. So non-basic variable, and here the basic variable are, for this point basic variable are s1 s2 s3 s4. Basic variable are s1 s2 s3 s4. In the b what we have the x2 as a 0, and s1 as a 0. So they are the non-basic variable, and here the basic variable are x1 s2 s3 s4. So here you can observe from the pool at the point A, basic variable are s1 s2 s3 s4, and in the pool at the point B, basic variable are x1 s2 s3 s4. It means x1 is what, entering variable, s1 is what, leaving variable, right? So this is the leaving variable because it leave the basic variable pool. So it is the leaving variable, and x1 is the entering variable. So in every corner, at every corner, number of basic variable will be always 4. So here we have the replacement, here we have the replacement. So one is the entering variable, another one is the leaving variable. Now let us assume we have the solution space like this. For any problem, we have the solution space like this. Consider the 3-dimensional LP solution space in figure 3.4, whose feasible extreme points are A, B up to the J. Which following pairs corner point cannot represent the successive simplex iteration? So here you can say AB. So whether the AB are adjacent on the same edge, they are the neighbor point over the same edge. Yes, so it can be the simplex iteration. Then we say BD. So BD means this is the B. So directly you cannot go. You have to go through G, then this, right? So directly you cannot go. So BD is not a valid simplex iteration. Similarly, EH and AI, right? EH and AI. So EH you have to go through this, then this. So directly you cannot go. So EH is not a means directly you cannot go. Directly you cannot go. Then AI, So AI, so this is the A, this is the I, directly you cannot come. So it means they are not valid the simplex iteration. Always the valid one is the corner to corner through the edge. Suppose the simplex iteration start A and the optimum occur at the H. Indicate whether any of the following path are not legitimate for the simplex algorithm. So A, B, G, H means you have to start from the origin and up to the optimum point you have to reach. H is the optimum point. So in this case, A, B, right? A, B. Then we have the E, A, B, A, B, G, H. A, B, G, H. So this is the A, B, G, H. No jump. Always corner to corner through edges. So that is the valid iteration. That is the valid iteration. A, E, I, H. If you say A, E, I, H, so A, E, we have to go through the jump. So that is not a valid. That is not a valid, right? Then A, C, E, B, right? A, C, E, B, then A. So here we have the A two times. That is not a part of the simplex method, right? In the simplex method, the same corner point will not come. So that is also not a valid simplex iteration. No, because the path returns to previous extreme point. So that is not a valid extreme point, a valid simplex method. It is also not a valid simplex method, but this is the valid simplex method. Consider the solution space uh, in figure 3.4 where the simplex algorithm start at the point A. Determine the entering variable in the first iteration together its value and improvement in Z for each of the following objective function. So in this, if it is a question of the maximization, if you do the unit increment in x1, x2, x3, which variable will give you maximum improvement? Which variable will give you maximum improvement? Anyone?
X3, sir.
X3, right? So in the direction of x3 you will move and total improvement will be the 3. Total improvement will be 3. Similarly, maximize 5x1 plus 2x2 plus 4x3. So in the direction of x1 you move and improvement will be the 5. When we have the maximize z is equal to minus 2x1 plus 7x2, so in the direction of the x2 you have to move. When we have the maximize z is equal to x1, x2, x3, so x1, x2, x3 means we have the tie. So in any direction, you can start. In any direction you can start arbitrarily, right? Arbitrarily, you in any direction you can start. All will give the same improvement. Clear? All will give the same increment, improvement. So whenever we have the tie, always we break the tie arbitrarily. So that is the some important concept. Then we have the simplex method fundamental. So in linear program, the feasible solution space is set to form a convex set. I think this is in the chapter 7, right? Chapter 7 or chapter 8. This is the means chapter 7 part. But we require to study here before the simplex method. So in linear program, the feasible solution space is set to form the convex set if line segment joining any two distinct feasible point also fall in the set. Means if we have the space, so you take any point, and if the line joining these 2 points lie completely in that set, then that set is termed as a convex set. So here you can see, first one is the convex set. You take anywhere, any point, right? You take, and the line joining that those point will lie in that set. So that is the convex set. But in this case, in the example P, if you take this point, and if you join, so partial line will be outside this set, then this will be the non-convex. So that is the definition of the convex set and the non-convex. Then after, we have an extreme point of the convex set. Extreme point of the convex set is the feasible point that cannot lie on the line segment. So extreme point, this extreme point, right? This extreme point, all are the feasible point, but never this point lie the two joining of the two feasible point, never it lie over the joining of the two feasible point. So that is written, cannot lie on the line segment joining the two distinct feasible point in the set. Actually extreme point are same as the corner point. Extreme point is nothing, it is the corner point. That is another property. And mathematically, in the graphical LP solution given in section 2.3, we demonstrate the optimum solution can always be associated with the feasible extreme or corner point of the solution space. I have told you, always the always the solution exists at the corner point. It means corner points are important points. Corner points are important points. And what is the here importance thing? All the infinitely many points, all the infinite, you take any point, in the convex set, all the infinitely many points can be written as convex combination of the extreme point. Let this is the x1, this is x2, this is x3, this is x4, this is x5, and this is x6. And here we have the arbitrary point x, any point. So this x can be written as convex combination of the extreme point, means lambda 1 x1 plus lambda 2 x2 plus lambda 6 x6, such that lambda 1 plus lambda 2 plus lambda 6 is equal to 1. That is the convex combination. So here only it is written the same thing. Any arbitrary point can be written as convex combination of the extreme corner point, right? So what is the convex combination? Means here you multiply with the alphas, and alphas are such constant between 0 and 1. All the alpha lie between 0 and 1, such that their sum is equal to 1. Now let us have few questions. So that the set Q x1 comma x2 such that x1 plus x2 less than equal to 1, x1 greater than equal to 0, x2 greater than 0 is convex. So here we have the x1, and this is the x2, and x1 plus x2 is equal to 1. This is the line of the x1 plus x2 is equal to 1. So on this side we have the x1 plus x2 less than equal to 1. If you take arbitrary any point, graphically, if you take arbitrary any point, so all the line segment joining these 2 points completely lie in that set. So we say it is the convex. So how we can prove mathematically that this is the convex set? Graphically it is okay, but sometimes if we are not able to draw the graph, then how we can prove? So we assume that there are 2 points. Let's say it is the x1 bar and x2 bar. This is the x1 bar, x2 bar, and this is the x1 double bar, and this is x2 double bar. So these are the coordinate of the arbitrary any point in the convex set. So means we say that x1 bar and x2 bar lie in x1 plus x2 less than equal to 1, it means it satisfies the condition x1 bar plus x2 bar less than equal to 1. Similarly x1 double bar and x2 double bar also lie in the convex set, so it will give you x1 double bar plus x2 double bar less than equal to 1. Now the line joining means it will become, let's say it is the x1, let's say it is the x2, so line joining, so lambda 1 into x1 plus lambda 2 into x2 should right, it is equal to 0, right, it is equal to 0, and lambda 1 plus lambda 2 is equal to 1, and lambda 1 lie between 0 and 1. Similarly lambda 2 also lie between 0 and 1. So here we see, let x1 x2 bar greater than equal to 0, x1 double bar x2 greater double bar with the 0 be the two distinct point in Q. So it satisfies the condition. Now for the lambda between 0 and 1, any arbitrary point means, what is the meaning of the any arbitrary point? The point on the line segment joining the 2 points, right, two distinct point. So any arbitrary point can be written as lambda into first point plus 1 minus lambda, that is the lambda 1 and lambda 2, such that lambda 1 plus lambda 2 is equal to 1. That's why we have taken the lambda and 1 minus lambda in second point if they are greater than equal to 0. So that can be written as x1 plus x2 is equal to, right, lambda x1 bar plus 1 minus lambda x1 double bar lambda x2 bar plus 1 minus lambda x2 double bar. So lambda, if you will take common, here we have the x1 plus x2, right. If you take 1 minus lambda common, here we have the x1 double bar plus x2 double bar, and that is nothing, that is the less than 1. It is nothing, it is the less than 1, it is also less than 1 because it lie in it is the part of the convex set. So here we say that x1 plus x2 less than equal to 1, right. So we say that the line joining, we say that in the convex set, the line joining, right, in the line joining these 2 points completely lie in that set. So here we have taken the x comma y arbitrary point, here we have taken that x1 bar or x2 bar, here we have taken that x1 double bar and x2 double bar, and here we have the x bar and, right, xy, you can take any point, or x1 x2, right, or the you can take the x1 x2. Clear? Now next question, so that the set Q x1 comma x2, x1 greater than equal to 1 or x2 greater than equal to 2 is not convex. So when we have, this is the x1, it is given to you x1 greater than equal to 1 means this side area, x2 greater than equal to 2, x2 greater than equal to 2, this side area. So this side area is the convex. If you take arbitrary any 2 point, so whether the line joining these 2 points completely lie in the convex set, in the shaded region? No. So if it is no, then it is not a convex. So here we have the shape. So the line joining these 2 points not lie in the convex set, so that's why it is not a convex set. So again we have considered the same thing. Let us have x1 bar x2 bar as a 1 comma 0. So this is the 1 comma 0 and this is what, 0 comma 2. So we assume as a x1 bar x2 bar x1 double bar x2 double bar, right? Both belongs to Q. Both belongs to Q. Now we take arbitrary any point, right? Arbitrary any point x1 comma x2. So we take the convex combination lambda into first point plus 1 minus lambda into second point. So it will give you lambda and 2 minus 2 lambda, where lambda lie between 0 and 1. So by chance, if you take lambda is equal to lambda any value less than 1, lambda any value less than 1, right? So less than 1. So it will give you, right? It will give you 2 minus 2 lambda, lambda less than 1. Yeah, it will come x1 less than 1 and x2 will come less than 2. What is given to you? You have x1 greater than equal to 1, x2 greater than equal to 2. But when we take lambda less than 1, so here any value less than 1, it will give you x1 less than 1 and x2 less than 2, which contradict the Q. Means x1 x2 you can say does not belongs to x1 x2 does not belongs to set Q. Clear? Determine graphically the extreme point of the following convex set Q is equal to x1 comma x2, x1 plus x2 less than equal to 2. So here we have this is the line of the x1 plus x2, right, is equal to 2, and this side area is what? X1 plus x2 less than equal to 2. So coordinate will be the 0 0, coordinate will be the 2 comma 0, coordinate will be the 0 comma 2. If you take arbitrary any point, x comma y, so arbitrary any point x comma y can be written as convex combination of the extreme point, convex combination of the extreme point, convex combination of the extreme point. Lambda 1, lambda 2, lambda 3 all lie between 0 and 1, such that lambda 1 plus lambda 2 plus lambda 3 is equal to 1. So here we have arbitrary, we take any point x1 bar, x2 bar as this. So when we take the convex combination, right, x1 bar, x2 bar is equal to lambda 1 0 comma 0, lambda 2 plus lambda 2 into 2 comma 0, lambda 3 into 0 comma 2. So that will give you 2 lambda 2 comma 2 lambda 3. So and here we have the lambda 1 lambda 2 lambda 3 greater than equal to 0 but less than 1, such that lambda 1 plus lambda 2 plus lambda 3 should be, right, 1. Last question for the today. In the solution space in figure 7.2, drawn to scale, express the interior point, 3 comma 1. This is the interior point 3 comma 1 as the convex combination of the extreme point ABCD. This is the extreme point A. Coordinate is the 2 comma 0. This is the B 6 comma 0, and C is the 0 comma 6, and D will be the 0 comma 2. 0 comma 2. So they are saying that whether any point 3 comma B 3 comma 1 can be written as a convex combination of the extreme point. So let us see. So here we say it is the F point. So this we if you extend if you make the parallel line through the F, right, parallel line with respect to x-axis through F, so it cut the E and it cut at the point G. So E is what? E is the middle point of the A and D. It is the middle point of the A and D. And what is the G? G intersect, G divide the line joining B and C in the ratio of 5:1. Right? So it will become 5/6 B plus 1/6 C. 1 by 6 C. And what is the F? F is the middle point of the E and G. Middle point of E and G. So E is what? Half of the A plus half of the D. And G is what? 5 by 6 of B plus 1 by 6 of the C. So when you put these value, it will come 1 by 4 A plus 1 by 4 D plus 5 by 12 B plus 1 by 12 C. So here you can see 1 by 4 between 0 and 1, lie between 0 and 1, lie between 0 and 1, lie between 0 and 1, and their sum is what? 1 by 4 plus 1 by 4 plus 5 by 12 plus 1 by 12, that is equal to 1. Means the uh, the point 3 comma 1, the point 3 comma 1 can be represented as a convex combination of the corner points A, B, C, D. So in next class we continue this part. So for today, any doubt, please? From today lecture, anything?
No, sir.
Okay, thank you. Have a nice day.
Thank you, sir. You too.